Okay, let's see if I can keep this short and sweet. So this is a screenshot of what we're going to look at in the background. This one here. I want to think of the lies in engineering. So the lies in engineering is that mid-spans are the loads divided equally on each support. So 10 pounds here. And let's do 10 pounds. We'll just do 10 pound load. All right. So 10 pound load as and this one as she believes results in a 5 pound distribution here and a 5 over here. So that's it. All right. Now watch. Before I tell you how, can you tell me how this can be defective in thinking? How can this be defective in thinking? It's dead center. Dead center. Everything's dead center of this span. And don't think I'm being devious with anything with this overhang stuff. No, just dead center. All right, so the how can this be so? Well, let's go ahead and grab some steel now. And steel can also be the concrete could behave this way also. But now, ooh. So let's grab some steel. Let's just put it in here. Oops. Wasn't ready for that yet. Let's put some steel at the top. Oh, let's put some steel over here. Now let's go ahead and do that. Overlap. So there's our overlap. All right, you see what's going on defective here already? This is the top steel, which is I ran it all the way across. Now the bottom steel will run. We'll just run it across. All right, we'll just do that. So I want you guys, and I won't anchor it down or anything else. We'll just look at it like this. So what's going on here? Will this side of the concrete behave as the same as this side of the concrete? No, it will not. It will not. One will be more stiff than the other side. One will be more stiff than the other side. The overlap right there. Okay. This is where your potential failure can happen. This is also where you get extra grip force if you don't have a problem. Your mid-span of so from here to here, you've got your continuous steel, but you also got some steel over there. Let's change this to 5 kips, or let's change this to 5,000, and let's change this to kips to 5,000, right? And we'll change this to 10 kips. All right, so now we're going to start getting some reactions. What will happen? How will this behave? Well, the bottom steel matters also. The bottom steel matters also. That's continuous. What if I get rid of continuous and I do it like this? This time, this steel is the further steel over. And this time, the steel for the bottom is over here like this. Did they just cancel each other out? Nope, I don't think so. The reaction is going to be different based on the steel placement. And then I'm going to do something a little different here. I'll just grab it. So they would have to have it perfect, but let's say they profile the steel like that a little bit. It's a little bit of on a pitch or slope. Cant, as I think of it right here. So will both sides behave the same? No, this side has a anchorage point that's higher. This side's point is now lower here. This side is down here. This anchorage point that's higher I'm referring to is over here. This is the lower point is what I meant when I said this side. So there we are, almost balanced, and we'll do that. Now let me have a little more fun. Now let's consider the structure here. Well, this structure had a pinned wall here system. It was pinned, and in fact, I'd argue that, not in fact, but in my representative theory, I argue that the top steel and bottom steel, see how they're ending like that? They're kind of engrossed like this, turned on their side. Maybe that's the bottom steel, and maybe it's the top steel. So you get this little bypass look. It's over here. You can get deep into the images. You would find two pieces of concrete ruts like this, maybe like that, and like this, that we can observe. I'm not saying they're not equal lengths. I'm just showing you it's right about there somewhere, and it turns a little more of an angle. But that gets you, well, wow, it gets you kind of a hook, doesn't it? So let me just do a hook here, take a little liberty and give you a hook. All right, so let me give you a hook. And this securement at this end is much more significant than out here at the column. We'll call these one of the columns here. This column is having to take the load, so that wall, this little staple thing, that's entire continuously. Here is the column sticking up. It's got to take the load all the way from this side all the way over to there. ACI states that you only pretty much use 2 panels, whatever. All right, is this foreseeable collapse? Yes, it is, because I've always argued that as long as its concrete is engaged with another section of concrete, it can pull it down, period. It can pull it down, unless it becomes at rest. That's when it loses its momentum to be able to pull and keep pulling. So it becomes at rest, and that's it. It's out of gas. So you see, quite often you'll see the parking garages fail, and you'll see that it didn't engulf everything. Well, because it became to rest. It lost its energy, or these double T-beams, and they just separate. And so they create what I call a shear plane. And you can call it a fracture plane, but there's no real fracture there. It's a plane. So then we go to, on this side, well, they did some little rabbit ears, 12-inch, I believe this is roughly 12-inch extension here. So there's a 12-inch. That's it. They do 4 of them. Remember, they go 2, and if we're looking at it from the top, you get 12, you get 2, you get 4. And the orientation. And it's set like that. Yeah, I can go with that. Too bad this won't go on top of it. But there's 4 pieces there. And maybe 2 more, apparently, what I've observed, you get 2 more pieces. You get that continuously across the slab in this direction. This direction is where the 2 cross over the heads. But back here we have these links, top and bottom steel. All right, let's work our way to this fracture right here. And let's talk about how I'm calling the engineer out on her false beliefs. So this side, imagine they're cantilevers now. Let's go ahead and do what people like to do. Let's go ahead and divide this. There's my fracture. All right. So there's my fracture. I'm just creating one. And so you got your dip here. So the strain on this side, this top steel is not connected to this bottom steel. But over here, it's connected with more bypass with these 90s, I believe, over there. Let's talk about cantilever ability of it. What I mean by that is this steel makes for a rigid connection. This hoop makes for a rigid and top connection. I don't want to give it all away. Don't want to give this away. Maybe I do. I'm just trying to think about it. I really don't want to give it away. I want you guys to figure it out, what I'm trying to say. I'll give you some hints, and I'll work my way up to it maybe around 4 videos from now. I'll give it to you. I've already posted it, so if anyone nails it, I'll reveal the video. It's already posted, but not. It's in the private room, or it's not posted to the 4th. But it's in the private room also, I think. But this detail, how it behaves. But remember, gosh darn it, I don't want to give up everything, because it's weird. You know the amygdala, you was something you own. But then I had my man Phil here come on here and told me, look, just let it go. He's been robbed more than not. Let it go and just share. Be happy that you're sharing, that these that the engineers can learn, but of course they can't complement or triangulate back to where they learned it from. They got to pretend like they're geniuses and came up with themselves. As far as I know, I'm the only one that's stating concrete is equal in compression and tension. I guess you could argue that by default, everything is equal and balanced and equilibrium. And funny thing, statics talks about that. But when we get to concrete, all of a sudden, people can't remember their own static lessons about being equal. They're like, no, the ACI states that concrete is stronger in compression and weaker in tension. The values being 10% of the value of the compressive load would be the tension forces they can take. Well, that's not either tension is not the opposite of compression, or you're putting your meters and you're registering your meters in the wrong location. Perhaps you shouldn't be registering it there. So now you're here. The way they do the testing is terrible. It's defective. I really want to. So if that's true, then why are all engineers, ACI, and the entire world using tension as a structural element if it's so weak? Watch how simply I prove it. Here's your top steel, here's your bottom steel. What holds those two pieces of steel together in this plate slab construction? What holds the two of them together? Concrete. What holds the two of them together, I ask you again? Concrete. That's it. Concrete between the top steel and bottom steel. And that would be what? That would be depending on the concrete to be in tension, to work in a tension capacity to hold this top steel and the bottom steel together. That well, it's more than that, some reactions too, but what's holding this top steel and bottom steel is tension. Now, if you use some hooks like this and make some stirrup systems in it, now all of a sudden you're engaging your top steel and bottom steel. All the way down is what I recommend in all pads that you do if you're going to do it. Engage it. Stop playing around. Stop saying concrete's weak in tension and then don't engage it. Make a beam. Make this plate a beam. Now, nobody says it's going to be easy. Maybe you got to start, come up with a faster system. I got one more little giveaway for you. So where it meets the back wall in this column, and this column meets that column, not only the stirrups, but make an internal truss system. This is what I was going to release on the 4th. Make an internal truss system. Okay, so this is something you can prefab somewhere. Make this internal. Tie it together. There's your hooks, your links. It makes this rigid. And I'm not saying you have to do it everywhere, but at least make a internal beam there, like you see out in Texas. They'll do it, the drop beam. But make it internal to the deck. And then internal back here also. You're going to have to change your rebar configuration once you do this because the stiffness becomes greater there. And the deflection matters in this beam, this design here. Frankly, I'm not one for deflection. If you're going to have deflection, then you must have flexible joints and joints that are willing to fail. Because the stresses created in deflection have a reaction on the outside walls. Now, I do my force multiplier video for you guys, and hopefully I won't forget to show it to you again. But down here, a shear link was created. Right here in the back while they overlapped. It looks similar to this. It's a linkage created. That makes it more stiff back there. This whole zone back here acting more stiff, including the tie down here. This starts getting a stiffness, acting like a cantilever. And I'm going to take some liberty here and drop this down. I'm going to change the color. And let's change it to blue. So that creates a stiffness here that's greater than that's stiffer on this out from the wall out. So from the wall out, it's stiffer here than from this silly column outwards. So your stiffness is greater here. So if the stiffness is greater, this doesn't quite get to the 5 pounds exactly. It's intercepted, I call it. So part of the loads, in this case, we're going to get a deflection. And part of those loads are first taken on here. It's resisted here. And like the puncturing columns you see with the head still on up there. That's the critical shear area that still maintains. That's because of the stiffness factor. It's so stiff that it transfers over there and it's able to hand it off pretty much right about here and over because it's just rigid. It's just like having a damn bracket in it, if you will. Let me put a bracket here. Thank you, girls, for the shout out. Everybody's going to appreciate that. So it's like having a bracket here. Let's do that. Now let me take some liberty here. So which one do I want to take liberty with? I can't take any liberty. All right, so you see this here, right? Maybe I can. So it's like a bracket. So the force is over here, and over here there's this little head here, and so it's a very small bracket, very close to the column, and it's shared by 4 directions. This just comes straight back, sharing straight back, a little lateral, but all the way laterally it has a joining member 12 inches away, helping transfer that load every 12 inches down the wall, transferring it in this capacity, the stiffness factor. Now let's go ahead and try to prove that a bit. So my theory is, here's the column, here is the wall, and this rigidity is out here because of the configuration of the steel. And I would estimate it's about 5 foot out. And what do we have? We count about 5 tiles out, and you get a fracture plane all the way down. This looks like a control joint of some type. It was added for whatever reason. I don't know. But we don't see any at least, I don't know. I don't have a photograph there. I remember there was one at one time, but it was shared by the Miami Herald. I don't know what doctoring they might have done to it, if any at all. So here's our shear plane. So the stiffness here. So it didn't, when the deflection was taking place in this deck, I believe this. So I'm going to overlay this with a color. Let's do a heavier color, and let's use this funky color here. Let's up the size. So when the deflection was taking place, I'm going to go from this mark here to this mark. And so I'm going to do this. Oh, great. So let's put that down there. I don't need it. And we'll put that behind it. So let me do this. So let's call that the deflection, exaggeration perhaps. And you have the strain is here at the 5 foot mark out. So now you're getting your deflection is resulting in a deflection here and not back here at the wall. It would be a smooth break if that were so. And only smooth break I see from the columns, from the butterfly zone, if you will. Let's see, so here's the butterfly is over here then. It just, and considering the columns intercept it also. But it's smooth down there. And over here it ramps up pretty good. Remember, you got some car breakage. When it came to rest on the cars, it crowned some of those materials. But before it hit the cars, it already created that stress here, the stress loading at this plane here, tugging, so tug, tugging here. Upon tugging there, it created reaction, that rotation I talk about, and you get the force multiplier, the fracture, and you get it able to snatch out there just like you snatch a. So this is where I show this video here. It's called Concrete Deflection and Deck Tension. Half, I'm saying half, question mark. Also has a huge compression force multiplier at the wall. So you got to find this video. And I want you to think of this video right now. And I want you to put 5 pounds, 5,000 pounds, whatever. I want you to put it right here at the wall, at here where I have that steel, thread, all thread. And you put it right here, that load right here. What happens? It just transfers in shear straight down pretty much. It's right above there. But what happens when I put it out here at the far end? When I put it at the far end, it has what? It's no longer a straight parallel to the wall fracture. Let me get rid of the volume. It's no longer your weight being here would just shear this off, and this would just pop this. Putting a weight here would load this on top of that steel and try to transfer through the steel back into the wall system there. And if it could shear it, it would. If it could use the weight of the concrete, the ability of it, or the concrete would shear around the steel and come up, and we'd have it all fractured off. We don't have that. It came right from the wall, beautifully so. All of it just removed it from there. All the cones are revealed. Excuse me, my stomach growled. Now imagine the weight down here. When I do that, you can see the gap here. It's going to create a reaction at the bottom and tension at the top, pulling at the top, a tension, a pulling moment, but a compressive moment at the bottom against here. Yes, I said it. How do you get compression in the bottom where it's supposed to be tension? Well, I'm showing you now. Oh, my darn space is running out on my computer. If I let this keep going, it's going to hang up on us. So this will be part 1 then. Hopefully you'll follow this, and love you guys. Bye.